let's consider what happens to a charge when it moves in a magnetic field. Okay, like in this case, what if we have a charge coming in here in this region where we have a magnetic field, in this particular case pointing into the screen, perpendicular to the screen. But before doing that, let me go to a simulation. Okay, so this is my charge, see it here, and I'm going to be able to set a magnetic field. The charge has a velocity along the x-axis. I'm going to set a magnetic field along the color here. I'm going to set it along the z-axis, up along the z-axis. So now let's see what's going to happen. And you notice there, that's the effect of the magnetic field on the charge. Let's reset it. Actually, let's fully reset it. I'm going to have no magnetic field and see what will happen to the charge if there is no magnetic field. It moves on a straight line like we expect it to be. Okay. Now let's close. Okay. Now I'm going to set again the magnetic field. Play. And it goes around in a circle. Now let's show the magnetic field. Okay, there's the magnetic field at the position of the charge. It's pointing up, like I mentioned. You see it is the green arrow. Now let's show the magnetic force. See, the magnetic force is always perpendicular to the magnetic field. And you notice it is always pointing towards the center of the circle. It is actually quite large in this case, but it's pointing towards the center of the circle. Now let's do the right hand rule. Okay, let me go to a place where it is easy to visualize things. Okay, for example, in this case, the velocity, it is this orange vector. It is pointing in this particular case towards the right of the screen. And then the magnetic field is pointing up. So you hold your hand with your thumb pointing towards the right of the screen, and then your fingers pointing towards the top of the screen, and you'll notice that your palm is pointing towards the middle of the circle, like we observe it. Now if we go a little bit further up, now here the thumb should point perpendicular to the screen towards you. Your fingers are still pointing up, so your palm is pointing still towards the center of the circle. Okay. Now the key here is the magnetic force is always perpendicular to the velocity. Because it is always perpendicular to the velocity, it does no work. Remember the equation for work, it is Fd cosine theta. In this case, cosine theta is 90 degrees, so there is no work. Which means it does not change the energy of the system. Also, because it's perpendicular, it does not change the speed. In other words, the speed is constant, no change in kinetic energy. And we have circular motion. Now, using that fact, we can write the fact that we have circular motion at constant speed. We can write that the centripetal force acting on the charge is given by mv squared over r. The centripetal force here, we don't have any other forces acting along the horizontal except for the magnetic force. So that magnetic force, qvb sine theta, should be equal to mv squared over r. Now, noting that theta should be the angle between B and V, B, like in this diagram here, is perpendicular to the screen while V is parallel to the screen. So they are perpendicular to each other. So sine of 90 is equal to 1. And our equation becomes QVB is equal to mv squared over r. Solving for r, that's what we get. That's the radius of the circle. So in this equation tells us if I increase m, I'm going to get a bigger radius. If I increase v, I'm going to get a bigger radius. If I increase b, I'm going to get a smaller radius. If I increase q, I'm going to get a smaller radius. And you can try all of these out with that simulation. You know, for example, if I'm going to increase m, you see the bigger circle. One argument that you might think of, why do we have a bigger circle? It is we still have the same acceleration. I'm sorry, not the same acceleration. We still have the same force. The magnetic force is QVB sine theta. It does not depend on the mass. It's the same force, but I have a bigger mass. Bigger mass means I need to have a smaller acceleration. V squared over r has to be smaller, and that's why we get a bigger circle. Okay. One application of this is in particle physics, where we have particles to try to figure out the constituents of basic matter. What we do is we make particles collide with each other. And the results of these collisions are going to be particles that are going to survive for a very short time, time in the length of 10 to the minus 10 seconds or 10 to the minus 15 seconds. So very short-lived particles. But we can figure out some of their properties by subjecting them to different things. Among the different things we can subject them to is magnetic field. So like in this particular case, particles just after a collision are subjected to a region where there is a magnetic field. And you notice here, for example, if we look here, we have some particle that's going to result into several other particles. Now this is one, this is another one, this is another one. The one that moves in a straight line is not affected by the magnetic field. If it is not affected by the magnetic field, if you recall the equation QVB sine theta, that means its charge is 0. It has a speed, we see it continue to move, so it must not have a charge. So that's a neutral particle. Now, however, some other particles like these, we see it spiraling. Now, spiraling tells me there must be a magnetic force acting on it. And then if we follow, we might see some other particles spiraling on this side here. The fact that spiral in opposite directions being subject to the same magnetic field, that tells us they must have opposite charge. One of them is positive, the other is negative, and we can figure out what type of charge based on the magnetic field that we subject the particles to. And then the size of the circle tells us, once we know what the charges are, it's going to tell us, it's going to give us information about the mass and the amount of charge.